In this problem, a heavy bar of length L is supported by a smooth semicircular channel of radius R. Our task is to determine the angle alpha that the bar forms with the horizon. This problem looks quite simple, but it's not as simple as it looks, and it also allows us to examine a lot of interesting aspects important not only to this problem but to many other problems. First, I would like to point out that unlike the majority of problems we have considered so far, in this problem, equilibrium determines geometry. In the majority of problems, for a given geometry, we had to evaluate equilibrium and determine forces. First, let me say that there are two possible scenarios. In the first scenario, the bar is short. Its length is less than the diameter. In this case, the bar will rest horizontally, somewhere below the floor level. On the other hand, if the bar is very long, the bar will still rest horizontally, but in this case, at the floor level. It is probably easy to see that if I consider this point as a pivot point, the bar on the left has to be shorter than the bar on the right for this form of equilibrium to exist, and therefore L has to be larger than 2 diameters or 4 radii. Finally, the interesting case is the one where the bar has an intermediate length between 2r and 4r, and that's the case which we're going to analyze. And for this case, the inclined angle is not equal to 0. Next, I would like to ask a basic question. How does the answer look like? In our case, the angle alpha has to be a function of L, R, and W. Let me point out that the first two arguments of the function f have the dimension of length, and the last argument has the dimension of force. Of course, the function itself has to be dimensionless simply because alpha is dimensionless. To this end, let me state a very important and very basic result. It's known as the Buckingham pi theorem. It says that the function f must have a proper dimension. In our case, the proper dimension would be dimensionless because alpha is dimensionless. And it has to be a function of dimensionless arguments. Now, if I look at the list of arguments R, L, and W, it is clear that the only way we can create a dimensionless argument is by taking the ratio of L over R. Of course, we can take the ratio of R over L, but the bottom line is we have just one argument. Why this is important? Well, obviously, we reduced a function of 3 variables to a function of 1 variable. How does it help us? Well, suppose you want to conduct experiments. And then, if you look at the function of 3 variables, then you have to test bars of different lengths and different weight, and the channels of different radius. In contrast, if I look at the last formula, I can use one channel, this fixes R, and then I can use bars of different lengths, the weight doesn't matter, and by varying the lengths of the bar, I can construct the function f experimentally. Thus, in this setting, I can get away with one channel and bars made of the same material. In this case, I may have to have multiple channels, multiple bars made of multiple materials. Finally, I would like to remind you an important result from geometry. This result involves a circle centered at O and an angle ABC. In this angle, all points belong to the circle. The result of interest to me is the angle ABC is equal to half of the angle AOC, and it is measured by half of the angle corresponding to the arc AC. A particular case of this result is that if AC is a semicircle, then the chord connecting A and C is equal to 2R, or a diameter, and then AC is equal to P and angle ABC equal to P over 2, or 90 degrees. I can state it in the following manner. If an angle is supported by a diameter, then this angle is equal to 90 degrees. Of course, this applies to inscribed angles only whose points are on the circle. Now I'm ready to proceed with a free body diagram. The only free body of interest here is really the bar itself. So it is subjected to the gravity force, and at A it is subjected to a constraint such that the force NA is perpendicular to the surface of the circle, and at A it is the circle that defines the normal. At B, the normal is defined by the bar, and again, because it's a frictionless contact, the force NB is perpendicular to the bar. You may look at these 2 points and recognize that both of them involve a contact of a smooth surface with a well-defined normal and a sharp corner where the normal is poorly defined. And in both cases, I choose the normal by looking at the smooth surface. This free body diagram looks very simple, but in order to quantify it, we need to identify the orientation of the forces involved, and we also probably need to know the lengths A, B. The only thing that is explicitly known right now is that the weight is vertical, and that the location of the weight is in the center of the bar, meaning that this is the midpoint. To evaluate this free body diagram, I would like to do some geometric constructions. Let me start by looking at the circle, and let me begin at the contact point on the left, and I would like to draw a line that starts at A, goes through the center, and ends at D. So AD is a diameter. Of course, this line is collinear to A. Next, I would like to connect the point D to the point B, and observe that in the triangle ADB, the angle B is equal to 90 degrees because AD is the diameter. Therefore, the line DB is perpendicular to the line AB. Now, I recognize that because DB is perpendicular A to AB, DB must be collinear to the force NB. Next, let me identify the angle of interest alpha on this diagram. To do this, I will draw a line through A, and this is the baseline, which is horizontal, so that this angle is alpha. Next, let me denote the angle BAD by beta. And my task is to find a relationship between alpha and beta. To do this, first I will draw a line between O and B. If I look at the triangle AOB, it is isosceles because both AO and OB are equal to R. Therefore, the angle OBA is equal to beta. Now, I observe that OB is horizontal, so is the baseline. Therefore, if I look at these two angles, alpha and beta, these angles must be equal. Now, let me summarize this result by redrawing this diagram and showing the angles as determined in the previous slide. In addition, I would like to show the location of the weight, and it is located at a point C. C is located at a distance L/2 from A. It is the center of the bar. Now it is clear that all the forces involved can be easily projected on the horizontal and vertical axis. For the force, sum of the forces on X, the projection of NA is dictated by the angle 2 alpha, the projection of the force NB by the angle 90 degrees minus alpha. For some of the forces on Y, we still have the same angle, 2 alpha and 90 minus alpha. In addition, we have the force W. Finally, sum of the moments about A engages the weight W. Its arm is equal to L/2 projected on the horizontal axis, so that the arm is half L cos alpha. The force NB produces a counterclockwise moment, and its arm is the length of AB, which could be calculated from the triangle ABD as 2R cos alpha. To solve this equation, first I will slightly simplify the first two equations by removing the dependence on the 90-degree angle, and I will obtain these two equations. The last equation for the moment can be simply solved for the force NB. Now I can substitute this equation into the first one to obtain the expression for the force NA. And finally, I can take these two expressions and substitute into the second equation, which will give me the following trigonometric equation. Please observe that the weight W is cancelled out. To solve this equation, I will use trigonometric identities to simplify both sides. For the left-hand side, I observe that I can use the trigonometric identity for the cosine of a difference of two angles, which simply tells me that the left-hand side is cos alpha. For the right-hand side, I will use the equation for the double angle, and now I can put it together and I obtain a quadratic equation for cos alpha, and I can solve it to obtain this result. Now, let me observe that the equation could be simplified if I simply set L over 16r equal to theta. Then cos alpha is equal to simpler expression as shown here. Now let me see what kind of theta gives me angle alpha equal to 1. Of course, I know cos alpha equal to 1. Of course, I know cos alpha cannot exceed 1. And the critical value of theta corresponds to 1/4, and it means that L has to be less than 4r. Please go back to the second slide and see that this is the critical value for L that signifies a transition from medium bars to long bars. Again, provided that L is less than 4r, I can express the angle alpha in this form. Now, I would like to present an alternative solution. I'm not going to start from the beginning. I will start from the diagram that involved the introduction of the angle alpha and the establishment of the fact that this angle is also equal to alpha, where we said that beta equal to alpha. Now let me proceed slightly differently. Let me start with the point D and draw a vertical line DE till it intersects the circle, and then connect A and E. If I look at the triangle ADE, I observe that the angle E is supported by a diameter. Therefore, it is equal to 90 degrees. Since DE is vertical, AE must be horizontal. It means that the angle EAB is equal to alpha. Next, I would like to use the point D as the reference point for the moment equation. The forces NA and NB intersect the point D. Therefore, their moments about D are equal to 0. it means that the moment of the weight with respect to d has to be also equal to 0. It means that the arm of the weight must be equal to 0. Since the line DE is vertical and it's at least parallel to the weight, then I conclude that the line DE must be collinear with the weight, and therefore the point C, or the midpoint of the bar, is the intersection point between DE and AB. Once this is established, I can calculate AE from two triangles. First, I look at the triangle ADE and note that from this triangle AE is equal to 2R cos 2 alpha. Second, I look at the triangle ACE and observe that from this triangle AE is equal to AC, which is half L times cos alpha. If I look at this equation, I can recognize that this equation coincides with the one derived from equilibrium equations of the previous solution. Thank you very much.